Recording in progress.
So I'm going to start discussion in just few minutes. Let me make sure that everyone is able to log in. And are there any questions at this point? Yeah, unfortunately, please don't send me emails via Canvas, because replying to that email is a little bit painful. So okay. So I'm going to start today's lesson. And today's lesson is going to be super duper important. And why this is going to be? Because believe it or not, in 15 minutes today, I'm going to teach you what you studied in your differential equations class. So you don't have to remember any techniques that you studied in your differential equation class, but I want you to follow a very simple technique, and we will talk about it in just a second. And then we are going to use that to solve linear differential equations with constant coefficients, linear differential equations with constant coefficients subjected to external excitation, and in some cases you can solve linear differential equations with periodic and quasi-periodic coefficients. So what I'm going to talk today is first and foremost the application of the eigenvalues and eigenvectors to solve problems, and that would make things abundantly clear. So first and foremost, we studied eigenvalues and eigenvectors in terms of characteristics of a matrix, because you get that by solving characteristic equation for the matrices. Now, where are they used? The extension of eigenvalues and eigenvectors is singular values and singular vectors. But in today's class, I want to talk about why this eigenvalue decomposition is very, very important in the context of differential equations. And there are many, many examples or many, many applications we will gradually work on. But the purpose of today's class is show you how this eigenvalue thing makes our life super duper simple. So what I want you to understand and is, once you understand eigenvalues and eigenvectors, what they are doing, you can solve any differential equation with constant coefficient, actually almost all differential equations with constant coefficient, with a very simple technique. And that is one of the important reasons eigenvalues and eigenvectors are used. Can someone tell me that if you have a matrix, A, and if this matrix is a square matrix, you can find out its eigenvalues.
New York, before coming here, I was there for like an hour, okay? I basically got down from the bus and I had to get into the
Eigenvalues and eigenvectors. So if you think about what we talked about, eigenvectors form a basis. And this basis is important so that we can resolve the components, or in other words, we can look into the hidden structure of the system. So I want to take a very simple example. The very simple example is, say, if I want to solve a differential equation. So x dot is equal to ax, and x is just a scalar. So I'll give an example, something like this. Dx by dt is equal to 5 times x. So this is an example which I want to solve. How would I solve this problem? This problem can be solved is something like dx over dt is equal to a times x, and a is just a number. In this case, a is 5. So I would write dx divided by x is equal to a times dt, and then I'm going to integrate left hand side and right hand side. Do you agree with me? So once I integrate on the left hand side, I'm going to have ln of x. So I'm going to have ln of x is equal to a times t plus a constant of integration c1. Do you agree with me? Now, but I want the relationship as x of t in terms of some function. So what I'm going to do is, I'm going to take an exponent on the left hand side, and I'm going to take an exponent on the right hand side. So this is going to become x of t is equal to e at plus c1. In other words, x of t is equal to e to the at multiplied by e to the c1. Now please note, e to the c1 is a constant, so I'm going to call this a naught, and x of t can be written as a naught e to the at. Do you agree with me? Do you agree with me? Very simple, right? Now, what I want you to do is, I want you to think about a problem where x is not a scalar quantity, but it's a vector. Okay, it's a vector. So the problem that I'm trying to solve, and actually I will solve a toy problem first, and then I will solve an actual problem so that it will make clear. So you'll understand what is going on. So what I want to do is, think about it. I have an expression x1 dot x2 dot is equal to, say, 2, 3, 4, 5. Yep, this was happening to Zoom all along. In the robotics class, same thing unfortunately happened. So my apologies. This is Zoom has been a little bit problematic today. So it has been dropping. Recording in progress. Okay, so the point here is I have an expression, something like 3, 4, 5, 6, and I have x1, x2. Now, what that means is this. If I were to rewrite this expression, and you believe me that this is not a trivial problem. Recording in progress. Okay, if Zoom crashes this time, I'm gonna use the whiteboard. Okay, can you hear me, my online students? Unfortunately, we are having Zoom problems today, so I am going to use the whiteboard. And my hope is that you would be able to see what I'm doing. Because later I want to use Matlab and then show some of these problems in action. You can move the table, but this table is not long. So, table can move. Oh, I think there are wires attached to it, so it can't move. Anyway, so the point Okay, let me take an example. I'm gonna write this example something like this. X1 dot is equal to 3x1 plus 2x2 and x2 dot is equal to, I'm going to say 5x1 plus 7x2. And what I have is I have these coupled equations. So I'm going to call this. So x1 is one variable. This is the first order differential equation. This is the first order differential equation. And these two equations I want to solve. So how would I solve this? Step one is to write these equations in matrix form. X1 dot, x2 dot is equal to 3, 2, 5, 7. And I have x1 and x2. If you look at the mathematical jugglery I did a moment ago, you will realize that I use the exponential operator, or I use the exponent and solve the problem. So I'm going to do the same thing, but I'm going to rewrite what I did here just for my reference. X dot is equal to ax. Okay. And what I did, essentially, the solution was x of t. This is super important. X of t is equal to a constant a naught e to the a t. Do you agree with me? But in this, and this is super important, if you understand what I'm going to do next, you will understand whatever you studied in differential equation, that whole thing gets captured in just one solution method. So can you see that here I have a matrix which is capital A, right? So I'm going to write down something like this: x1 of t, x2 of t, this is super important, is equal to, can you see that I had some a, okay, a constant. I had just one constant because there was one dependent variable. I'm going to have two constants because there are two dependent variables, x1 and x2. I'm going to have two constants because x1 and x2. But what that means in terms of solution, is I have e, instead of small a, I have capital A, multiplied by t, multiplied by, I'm going to call this x naught, which is sort of something like x1 of 0 and x2 of 0. And I'm going to pause here for a minute and let you ponder on this, what I just did. This is the scalar equation. This is a vector equation because there are two scalars, and this is e to the power at. Everyone understood this? This is, in theory, not the right mathematical operation. Why this is not the right mathematical operation? Because this is an exponent of a number, and this is very important. This is exponent of number, and this has to be exponent of a matrix of matrix. Now, what do you mean by that? What this means is basically, to solve this, I need to use expn at multiplied by x10 and x20. So the next question that comes in this discussion is, why is this needed? This is needed because with just, instead of finding the exponent of a number, if you find the exponent of a matrix, you get solution of x1 and x2. If you don't realize the potential of this, let me stick to Matlab and show you how this can be solved in just one line of code. So what I'm going to do is, I'm going to share my Matlab. Yeah. X1 of 0 is the initial condition of 0. The value of x1 when time t is equal to 0. Value of x2 when time t is equal to 0. What does that mean? And let me clarify this for a second. What is this A0? A0 is not, so think about it. If I substitute value of t is equal to 0 here, if I substitute value of t, you agree with me, this becomes x of 0 is equal to A0 e to the 0, which means 1, right? So what that means, if I were to plot x of t on y-axis and t at time t is equal to 0, this is my A0. And depending upon whether I have a as positive or I have a as negative, I would have an exponential growth or I have exponential decay. For some reason, if my value of a, if my value of a is 0, then what's going to happen? It's going to be a straight line. I'm going to write this down. This is a is equal to 0, a is less than 0, a is greater than 0. I'll try to. Okay. So that's what is happening. Oh, I didn't realize this is mirror, but you can see. You can see the actual boot. Yeah, but then they will see mirrored. Okay, so I don't know what to do here, but the point is, this is how it looks. This is how it looks. And I'm sorry about the issues today, but trust me, I will actually make a video lecture and upload the video lecture by this weekend, so you will have some nice reference. So, but let me explain what I was trying to do. Is you actually, how do you do this in Matlab? So I'm going to share my Matlab screen. And I will show you how it is typically done in Matlab. So if I have a matrix, I'm going to say SYMS T, because my T is the symbolic variable. I'm going to have my matrix A, and matrix A is going to be 3, 2, comma 3, 2, 5, 7. So I'm going to have 3, 2, 5, 7, and I want to find out the solution of this system. It's very easy. You would say EXPM in the parentheses A multiplied by T. And once you do this, you get a super complex equation, which you can say simplify. And then you'll get a very short, nice expression. And you may say that this is not nice, but this, believe it or not, this is the solution of this differential equation. That's all you need to know from differential equations class. However, one thing that I want you to note, that this is actually a matrix. So EXPM80 is a matrix. So this is a 2 by 2 matrix. When you multiply that by x1 of 0, x2 of 0, so basically 2 rows, 1 column, you can see the matrix multiplication works out nice. So 2 rows, 1 column. Can you see if you have 2, 2, and then you have the solution for x1 and you have the solution for x2. If you have Matlab, I would strongly recommend you to do this exercise. Now, what makes this possible? Why we are able to do this? This is because of the eigenvalues and eigenvectors. And I want to show this to you by means of an example. But before I go any further, if you have Matlab, I want you to obtain this super complicated long expression. And I want you to observe that this expression is actually the 2 by 2 matrix. When you are going to multiply those by the initial conditions on x1 and initial condition on x2, you are going to get only 2 rows. So you will have first row and you will have the second row. That is nothing but the solution of the problem. Everyone understood this? Yes.
I'm just curious. Inside these exponents, there's like square roots inside them. So
Yeah, I know there are square roots because those are the natural frequencies. So those are the eigenvalues basically. Just bear with me for a second, and I'll make this clear to you. So if you want to be a little bit more adventurous, and I'm gonna say this is gonna be x1 0, which is the initial condition on x1, x2 0, which is the initial condition on x2, you can actually do something like this. x1 0, then x1 0 semicolon x2 0, and now you can write, or you can actually run your Matlab. Yeah, you need to run the whole code. So you need to highlight this, run the whole code. And now, and I really want you to do this. Can you see that now you just have 2 rows? You understand? Now you just have 2 rows. The first row means this is the solution of x1 for all time t. Second one is the solution of x2 for all time t. From your differential equation class, can you relate how painful it would be if you were to use the techniques that you studied in your differential equation class to solve a linear coupled differential equation? Now the power is not just solving the problem with some mathematical technique. Now I want you to think about this problem for a second and what exactly is going on. And before I actually tell you where the eigenvalues and eigenvector come in picture, Did everyone get that answer? Yeah.
But, so you think that this is simplified, but isn't this because of Matlab?
This is because of eigenvalues and eigenvectors. And I will tell you in just a minute. Okay, just bear with me for a minute and I'll tell you. So this all simplification is possible because of eigenvalues and eigenvectors. And you may ask me why. So let's start with the very simple command for Matlab. M comma n is equal to, and I want you to do this along with me. A. Can you see that n is nothing but n are the eigenvalues and m is the eigenvector? Can you see that? Once you apply m comma n is equal to ERGA, m are the eigenvectors and n are the eigenvalues. Do you agree with me? Now I want you to do something what I'm going to do next and see what happens. I'm going to start with, and before we do it, I'm going to say inverse of m. Very, very important. Inverse of m multiplied by a multiplied by m. Inverse of m multiplied by a multiplied by m. And I'm going to say run. And what happened? I got the same eigen values on the diagonal matrix. Do you agree with me? I got the same eigenvalues. Now, let me pose this problem slightly differently. So I'm going to start with this problem that I have a matrix. And before I deal with matrices, let me give you the physical, what this physical problem is. Imagine if you look at the solar system that we have, and if you want to plot the trajectories of the planet, and this is a very important problem. So if you assume for some reason that Earth is at the center of the galaxy or center of rotation, and if you plot the sun and the planets, you are going to see something like this. You will see sun, something like this. Earth is at the center, but when you were to, if you were to look at the trajectories of planets, you can plot those, but they are going to look like something like this. And this type of behavior initially led to the assumption that the Earth, all the planets revolve around Earth. So this is Earth-centric trajectories, right? These are not the true trajectories. And if you were to try to find, this is exactly what happened. If you were to try to find the physical laws that govern the motion of the planets around Earth, those laws become super duper complex because the trajectories are complex. But here, what Kepler and other folks did, they actually assume to begin with sun at the center of the galaxy, sun at the center of galaxy, and all of a sudden, if you look at the trajectories become simple. What that means is once you change, and this is super important, the frame of reference, once you change the frame of reference, the derivation and interpretation of physical laws became super easy. What it means, you change the perception, you change from Earth-centric to sun-centric coordinate system, and then the Kepler's law can be derived very easily. Do you agree with me? So what I'm trying to say here is, perhaps to solve this equation, x1 and x2 is not the right frame of mind or right frame of reference. So what I'm going to do is, I'm going to do this. And I want you to go step by step with me, because if you have not done this before, this may be confusing. So what I'm going to do is, I'm going to say my initial coordinates are x1 and x2. Okay. Think about it like x1 and x2. These are the coordinates, assuming like Earth is at the center of everything. Okay. I'm going to relate. I'm going to use a linear transformation. Remember, this is a linear algebra course. So I'm going to use a linear transformation. I'm going to say this x1 and x2 is related to some other coordinate y1 and y2. So think about like x1 and x2 indicative of Earth center coordinates, and y1, y2 when the sun center coordinates. And I'm going to assume the relationship between these two is given by my eigenvectors 0.75, 0.65, minus 0.32, minus 0.94. And you may say, why this weird choice? What does that mean? It means my x1 linear algebra is a linear combination of 0.75 y1 minus 0.32 y2, and x2 is equal to 0.65 y1 minus 0.94 y2. Everyone understood this? What I'm saying here is perhaps x1, x2, these coordinates are not so simple to solve. So I'm going to assume this different coordinate system, y1 and y2, and see if they make my life easy. So what I'm going to do now, this is super important, x1 dot, x2 dot is equal to A matrix. I have this matrix A, x1, x2. And I'm going to call this matrix M. And you see my matrix is M. So can I say here x1, x2 is equal to M multiplied by y1, y2. You agree with me? This is very, very important. On the left hand side, I have the derivative, right? So I'm going to take the derivative of this guy. This n matrix is constant, so it's going to come out. So which means, can I say x1 dot, x2 dot, and if my online students can't see me, I want you to M y1 dot and y2 dot. You agree with me? I'm going to substitute this guy over here. M y1 dot y2 dot is equal to, A is going to remain the same. We cannot add dollars to pesos. So if I have y1 on left hand side, I'm going to have again y1 here. M y1 y2. Are you with me so far? Now what I want to do is, I would multiply left hand side by M inverse. I'm going to multiply the left hand side by M inverse y1 dot y2 dot is equal to M inverse A M y1 y2. And I want you to tell me, what is this guy? This guy is 1.25 0 0 8.74. Please try this and tell me if you get the same answer. Are you with me? Yes or no? Can you see this made our life super simple? Because if I multiply first row, first column, it's very important. First row, first column, y1 dot is equal to 1.25 y1, y2 dot is equal to 8.74 y2. This equation is exactly same as the scalar equation that we solved a moment ago, right? Which means without even thinking, I can write the solution of this guy is equal to y1 of 0 e to the 1.25 t and y2 of t is equal to y2 0 e to the 8.75 t. Do you agree with me? Now you may say all that is great, but our original expression is in x. We are solving in y. How do we go from x to y? Don't worry, we have this relationship that will take us from y to x. So what I'm going to do is, I'm just going to multiply by that matrix and I have the solution in x. And why is this mathematical jugglery possible? This mathematical jugglery is possible because, and this is where it relates, we changed the basis. What basis did we choose? We choose an orthonormal basis that actually decoupled the equations. It is like looking at the Earth and the planetary system with sun at the center. The things became super simple. And this is just possible because we used an orthonormal basis. And remember, in the very first class, we talked about the resolution of vector. So if you think about x1 and x2, x1 and x2 basis is something like this. But what we did is we stretched it. Remember, what does a matrix multiplication do? Matrix multiplied by vector, it actually rotates and stretches. Rotates and stretches. So what I did, I rotated and stretched so that I have y1 and y2. This is 1 and this is 1. So I had a basis x1, x2, and my solution space, or for that matter, differential equation, was expressed in terms of x1, x2. But what I did, I multiplied that by the matrix that allowed me to rotate and actually in this case shrink, because as you can see there is negative sign here. So I actually shrunk. So basically rotated and shrink the basis vectors so that now my solution is in orthonormal basis. What that means, and this is super important, I can independently resolve along y-axis, y1 axis and y2 axis. And that's exactly what happened here. Yeah.
How did we end up with, how did we land on the value for x?
Value for x1? Okay.
And
M. Oh, M. M, right? Oh, we just did. M is equal to EIGA, right? So M is nothing but the eigenvector. Matrix of eigenvectors. So we first did M comma N is equal to EIGA, right? So once I found out, so what I did, I used this guy to transform my coupled system of equation into an uncoupled system of equation. In other words, I actually rotated and stretched the basis so that it's very easy to solve. Do you agree with me? What's going on here? Believe it or not, this is more important than you think right now, because your entire differential equation course can be summarized in the steps that I just took. But then the next natural question is, what happens? This is can you see that this is the first order differential equation, only one dot. What happens if you have a second order differential equation, third order differential equation? What we would do is, no matter whatever is the order of differential equation, we will convert that into a first order differential equation. I'll give you an example. The example is something like this. You have a spring mass system. So this is mass, this is spring. You apply some force and let it go. What's going to happen? This mass is going to vibrate. You agree with me? I just showed you a horizontal mass, but same thing happens with a vertical mass. Mass, spring, pull the mass, let it go. It's going to oscillate back and forth. You agree with me? That is describing the motion of the mass. In other words, it is the solution of the differential equation. And I'm going to use Newton's law. Force is equal to mass times acceleration. Force is a vector. So, and I'm going to call this x dot, x double dot. So x is the displacement, x dot is the velocity, x double dot is the acceleration. As this spring gets pulled, I have force. That force is given by the stiffness, which is K, or this is force. This is K, and then this is X. So this is going to be Kx minus is equal to mx double dot. And probably you have seen this expression a lot of times. This becomes mx double dot plus kx is equal to 0. Before I proceed further, everyone understood that I applied Newton's law to derive this differential equation of motion. Deriving a differential equation of motion is not the purpose of this class. So if you don't understand the signage and everything, that's totally cool. But the key is, we have a differential equation wherein you have two derivatives on x. So the order is 2. And I want to solve this differential equation of motion. How many of you have spent some maybe half an hour or 45 minutes trying to solve the differential equation of this format? Perhaps your differential equation looks like this: 5x double dot plus 3x is equal to 0. Perhaps your differential equation look like this: x double dot minus 2x is equal to 0. Perhaps your differential equation look like x double dot plus x is equal to sine t. Have you seen differential equations like this in Math 275 or 265 or 275 actually? So can you relate to the pain and suffering that we had to go through in the first differential equation class to solve this problem? Can someone tell me, how did we solve problems like this? Do we remember?
Fraction.
Section.
Fraction.
Oh, this fraction. Oh no, no fraction. Assume functions. No assume functions. Anything else? So clearly we don't remember how we solved that equation. Okay, don't remember, that's totally cool. So here is what I'm going to tell you. So think about it. What I'm going to do is, I'm going to write this expression as a matrix expression. So my first variable is going to be x. My second variable is going to be x dot. Why do I need these two variables? Because the order of the differential equation is 2. And I need to express this as first order equation. So start with the 0th order, that is your first variable. Take the derivative of the 0th order, that becomes your second derivative, a second variable. And what I'm interested in doing is something like this. This is called as the state space. And I'm going to write this expression down as x dot d by dt. So first derivative of x is x dot. Do you agree with me? So I'm going to write this something like x dot. Second derivative of x dot, d by dt of x dot is x double dot. You agree with me? What is x double dot? X double dot is equal to minus k by m x. You agree with me? So I'm going to write this down as minus k by m x. So what I did, I converted one second order differential equation into two first order differential equations. But at this point, you may ask me a very valid question. This doesn't look like a matrix. And you're right. Right now it does not, but in a second it will. So d by dt x dot is equal to, I'm going to write this something like this, 0, 1 minus k over m 0 x dot. Are you with me so far? And for a second, I want you to treat this as the matrix A. And I can give you some numbers. So I can say my K is 3, my M is 5, and this is my matrix A. And now you can solve this system without any problem, right? Because I can do EXPM of A and get done with it, or I can find out the eigenvectors of this matrix and use something called as the modal transformation or the eigenvector transformation, or convert these basis vectors x and x dot. So I want you to think about it. I have x and x dot, x and x dot. They are perpendicular, but that is not the right coordinate system. So I can use another basis vector, say y dot, and find out the solution of y and y dot independently, and then superimpose. Yeah.
Just really quick, since you said dt of the vector x dot, wouldn't the x dot on the inside, on the other side, be x dot x double dot for that property, because of this is the second derivative.
So what I'm trying to say is, can you see this expression?
Yeah.
Are you clear with this expression? If I want to write this expression down as a matrix equation, you agree with me? This will look something like this.
This is the
Second row, first column.
state
First row, first column.
state space.
State space.
Yeah.
So what is the question? You have any question?
Yeah, we were using the equation systems optimization. It's just normally on the inside property, you would go, since you're deriving the outside portion, there would be over d, right? Isn't that what you're doing there? Or is it just there to?
No, what I'm trying to say is I'm trying to relate this
Okay.
equation with an actual example to show you the power of eigenvalues and eigenvectors. All this transformation. So as soon as I use eigenvectors as my basis vectors, my solution becomes super simple. And this is very, very important, because you don't have to study, or you don't have to remember anything that you studied from differential equation except what we did over here. that will solve almost all the linear differential equation problems that are not when there is no forcing. And if there is forcing, what do you do? A simple trick is you can treat this forcing as a state. So what happens is you can assume sine t is equal to p, and then you can assume p dot is equal to cosine t, and you assume cosine t as q, and then you will see that q dot will become minus p. And this jugglery we will talk about not in today's class, but we'll talk about this jugglery in next few lessons. So right now I just want you to understand that this technique can be applied when you have no forcing on the right hand side, or even though you have forcing, you can use the exact same procedure to solve the problem. And that is the power of eigenvalues and eigenvectors. Yes, question?
What happens if eigenvalues are imaginary?
Actually, in this case, you are going to get eigenvalues imaginary. If you want to find the eigenvalues for a second, if you use Matlab, you will see that these eigenvalues are going to be imaginary. They are not going to be real. And remember, so if you think about it, this matrix, so basically this, okay, let me see this. Do you agree with me that this matrix is not positive definite? This matrix is not symmetric, right? So since this matrix is not symmetric, when this matrix is not symmetric, eigenvalues cannot be real. Eigenvalues cannot be real. This matrix is not symmetric, and again, this is not positive definite. So that's why the eigenvalues cannot be real and positive. That is one of the tests that we talked about. If you have a positive definite matrix, positive symmetric, positive definite matrix, then only you are going to get eigenvalues that are positive and that are real. So in this case, this matrix is not symmetric. You can't expect to have positive eigenvalues, actually real eigenvalues. So that is what is happening. Okay. Once again, I'm gonna, any questions here? So please understand this concept will be very, very useful in lots and lots of classes that you take at ASU or when you go to industry. So if you want to solve a differential equation system, this is called as the coupled. Your question?
Then if the eigenvalues are not real, then after we can apply this rule to find x1, x2.
Yeah, so this rule, I mean, the process I showed you here can be used even the eigenvalues are real or eigenvalues are imaginary, doesn't matter. So this eigenvalues will become real if I do this, and then you'll see that you're gonna get positive eigenvalues and a lot of interesting things gonna start happening. But this technique can be used to solve linear differential coupled equations. If you have the first order differential equation or second order differential equation, you can still solve these problems. There is someone in the chat window. Yes, that is correct. Yes. Yes, Chiao, that is absolutely correct. Now, one issue that I want to talk about briefly is what happens if the eigenvalues are repeated. which means in this case, we found out two distinct eigenvalues. But in certain cases, eigenvalues could be repeated. In that case, the problem becomes slightly complex because you need to make sure there is an independent eigenvector. And I want you to think about this problem for a second. I said initially, to make our life easier, we are going to change the basis. So initially we were trying to work in the basis x1 and x2, but that was not an orthogonal. For that matter, it was not orthonormal basis. So that made our life complex. So I said, let's try to find out a basis. This is orthonormal. Okay. And since we had two independent eigenvectors, can you see that these eigenvectors, and I want you to do this for a second. Here in Matlab, I want you to say rank of M. Can you see the rank is 2, which means there are two independent eigenvectors. Do you agree with me? That's why I have a perpendicular basis. If for some reason eigenvalues are repeated, there is no guarantee that you will have perpendicular basis. You will notice that there is only one eigenvector. And if there is only one eigenvector, please understand it's not going to simplify our problem. We need two eigenvectors, or we need a basis, or we need two vectors which are perpendicular to each other, which are orthogonal to each other, and that can simplify the expression. Everyone understood this? That is the importance of basis. So, okay, any questions about eigenvalues and eigenvector? Repeat the last part. Okay. Imagine a case wherein the eigenvalues are repeated. Okay. Which means our eigenvalues are 0. So for example, what I mean by repeated is 1.25 here, 1.25 here. Okay, so eigenvalues are repeated. It can happen that for those repeated eigenvalues, you will not have two eigenvectors which are perpendicular to each other. And as soon as you do not have eigenvectors which are perpendicular to each other, then we lose the advantage that we have here. We cannot resolve them on one vector and other vector. So that could happen. It usually does not happen, but in special cases, it could happen. And we will look at those cases a little bit later. Okay. Yes.
The whole point is like, as you said, if the eigenvalue is repeated, that there's a possibility we might just have only one eigenvector.
Correct. Which means we not have basis. Yeah.
In case of imaginary eigenvalues, technically there aren't supposed to be eigenvectors in the first place.
No, there will be eigenvectors, because if you think about, let's try this, and I want you to try this. Put this matrix and find eigenvalues, and just exactly the same thing, EIG, and tell me you would get imaginary eigenvalues but real eigenvectors. Try this. This is very important. So please try this. So substitute this as your matrix. So this as the matrix 0, 1, minus 3 by 5, 5, and 0. I'm going to say A is equal to this. Evaluate selection. And I'm going to say EIG, so MN. Can you see that? So I have eigenvalues. Can you see the eigenvalues are imaginary, but they are complex conjugate, and basically I have eigenvectors. Now there is some physical interpretation to these eigenvectors. Basically, the eigenvector, this eigenvector, as you see, is the complex conjugate of the eigenvector. So you have an eigenvector here, that is the complex conjugate eigenvector. But these can be expressed as a real pair. Okay. Actually, I can show that to you, but I don't want to make things little more complex than they should be. But try doing M inverse multiplied by A n. Try M inverse and tell me what you get. Inverse M multiplied by A times M. Can you see I got the eigenvalues on the diagonal? Do you agree with me? Okay.
So, is this right? Let's say that in this case, the eigenvectors are inverted.
Okay. Just hold for a second. I'll explain that in just 1 second. Just everyone understood this? And clearly, the argument is, look, yeah, my inverse M, which is the eigenvalue, I mean, eigenvector is imaginary, right? However, there is a physical interpretation to this. And now what I want you to do is, M1 is equal to, I want you to take just first real component of eigenvector. So, and I will show it to you in just a second. What I want you to do is, I want you to take the real, so this is going to look like 0.796. Okay. Then I'm going to write here 0. Then I'm going to say 0.612. So what I did here is I took the imaginary eigenvector and just separated that eigenvector in terms of its real and imaginary components. And this is the perfect time to tell you something. Life in general is complex. Life in general is complex. It has some real components and imaginary components. So the problems that you deal with in life, they are complex. How do you solve a complex problem? Separate out the real part and imaginary part, and the problem will become simple, just like this. Inverse M times A times M. Oh, my bad. M1. So yeah, M1. Can you see what happened? I'll explain this to you. Probably you see something magical is happening, but may not be able to pinpoint exactly what is going on. So the point mentioned is absolutely correct. If I were to use Mn is equal to Eiga, Matlab is going to give me imaginary eigenvalues and imaginary eigenvectors. Do you agree with me? You agree with me? But the system under consideration, the system in point is not imaginary. It's a real mass, real spring. Do you agree with me? Which means it has something physical quantity. And what is that physical quantity? If it's just imaginary, I don't know. So what I'm trying to say is, just take those imaginary eigenvalues, imaginary eigenvectors, separate out the real part and imaginary part, and use that as the basis. And boom, what you got? You got the eigenvalues, but now the imaginary is no longer there because you have used the real basis. And again, there are advantages and disadvantages of using different type of stuff. But what I'm trying to say here is, The basis will make our life easy. I'm gonna wait here for a few seconds and let you ask me a question. This stuff is super duper important. Any questions? Yeah.
So the property of shifting the imaginary numbers into two separate columns inside a matrix is in order to not expand it out into higher level matrix. Like,
What do you mean?
I mean, like a 3x3 matrix.
No, it can be done for 3x3, 4x4, 5x5, 6x6. The problem occurs, so, and this is the problem we are not deal with next. What happens that you don't have the matrix that is described by 2 dimensions, but you have a tensor. Remember last time we actually did image read, and essentially we had something like m multiplied by n multiplied by s, or so we had sort of a brick of matrix. It was not a paper matrix, it was a brick. And then we tried to do SVD on, there was a student who actually tried to do SVD on 3-dimensional data and then tried to combine it and found out that results are not good. So in real practice, in real life, your matrix or your data is going to have 10 dimensions. You cannot visualize. So basically you can visualize brick, but you cannot visualize a hyperbrick, which means a brick with 4 dimensions, a brick with 5 dimensions, brick with 6 dimensions. But you still want your mathematical tools, SVD and everything, to work on that data. For that, we have to do something called as tensor decomposition, and that's coming next. But I want to ask you, can someone quickly tell me what are the key points that we discussed so far? If somebody asks you, hey, Edka taught you applied linear algebra for engineers, what did you learn? What would you say the first thing? The first thing, matrices are complex. How do you make matrices complex? The real life matrices are complex. You have to decompose them. So just like what I did, I said the problem matrix was complex. Separate out the real part and imaginary part. So what we did something called as decomposition, slice and dice. The most important decomposition that we talked about is called singular value decomposition, SVD. Where does the SVD come from? SVD comes from QR, which is wherein you have an orthogonal matrix and the row matrix, and then what you do is you have eigenvalue decomposition, which is that we just talked about, where you try to solve eigenvalue problems. The most important part is to solve matrices. We have to slice and dice them. You cannot eat an elephant unless you cut elephant in pieces. Everyone understood this? This is the most important part that we studied so far. Second part that we talked about is singular value decomposition is similar to eigenvalues decomposition, except singular value works for rectangular matrices, eigenvalues would work for square matrices. Everyone understood this? Those are the most two important parts. And then what we said, what is the benefit of singular value decomposition? The advantage of singular value decomposition is if you have, say, a million by million matrix, or think about it, million by million by million matrix. Out of that data, which part is the most important thing? Where you should focus? Singular value decomposition will tell you what is important, what is signal, and what is noise. So SVD is going to tell you what is signal and what is noise. And that is the key concept that we discussed so far. One thing I want to tell you is, before you come to next class, I would strongly recommend, if you don't have the textbook, get the textbook. The textbook is available in the bookstore. Read the textbook line by line. Even though you may not understand it, but try to read it line by line. if you get stuck, if you don't understand what the author is saying or what it means, ask me and I will explain it to you. That's it for today, and wish you all a good weekend, and I will see you on Tuesday. Okay, any questions from my online students?